Our title is Eye Gaze Capture for Preference Tracking, done by myself, Amrita, and my partner Pooja.
Our problem statement: eye gaze tracking has been for decades, and most of those methods are only through regression, which gives inaccurate results. This work is to implement eye gaze capture through deep convolutional neural network that automatically extracts the iris and pupil pixels of eye from input eye image patch extracted from frame images with SqueezeNet and UNet frameworks, and with the use of 3D eye tracking to detect which products the user sees.
Our project objectives are to implement eye gaze capture with the deep convolutional neural network and to detect user preference.
The system design contains firstly an input live video is split frame by frame. Then it is sent to produce image patch using Viola-Jones algorithm. The image patch is fed into a DCNN to extract iris and pupil feature. The extracted iris and pupil feature is then sent for eye gaze tracking, and the output produced is where the viewer sees. So for eye gaze tracking, the extracted iris pupil feature is sent to find the 2D pupil center and 3D eyeball center through calibration. Then 3D line projection from 3D eyeball center to pupil center is drawn, and eye gaze tracking is implemented.
This is our DCNN architecture. Our architecture consists of UNet and SqueezeNet framework. Here, our image is of size 24 cross 48 with a RGB image. Our input image is given to the UNet architecture. It consists of a convolutional layer in contracting path and transposed convolutional layer in expanding path. So in our architecture, convolutional layer in the contracting path is substituted with fire module of SqueezeNet, and a transposed convolutional layer of expanding path is substituted with transposed fire module. Here, max pooling layer is substituted with 2 cross 2 strided convolutional layer for efficiency. Softmax layer produce probability map which contains probability of each pixel that if it is within the iris pupil region or not. With this probability mapping in pixel classification layer, pixels are labeled as 1 if it is present in iris and pupil region or else 0.
Once the iris and pupil features are extracted, the pixels that are labeled as 1 are considered as points. A mean value is found for this point through mean shift algorithm. This mean point is considered as the 2D pupil center. Firstly, the viewer is asked to look at a predefined center point in the screen. Considering the eyeball center and pupil center are collinear, the pupil center is back projected to fix the eyeball center. Then the origin is shifted to the eyeball center. A 3D line is projected from the origin to the pupil center that keeps varying for each frame, and this 3D line is intersected on a plane. So the point of intersection of the plane and the line is found, and it is linearly transformed that to our screen plane, which is of dimension 1000 into 800, and the plane is of dimension 80 into 64. This is a convolutional neural network that is trained using a self-made dataset of 3040 images. Here, semantic segmentation is done for the input eye image patch. The pixels that are labeled as 1 are considered as points, and mean shift algorithm is implemented on it to find the pupil center. This code does the calibration for finding the 3D eyeball center. This code snippet does 3D eye tracking using the spherical coordinates. This code snippet finds the point of intersection between the 3D line and the plane. This is where both the equations are equated to find the point of intersection. This code snippet is for a linear transformation from the plane to the screen plane. A factor of 6.25 is multiplied to the point of intersection to plot the point on the screen plane. This is the output of the DCNN. From these labeled pixels, the points considered as points. So from these points, the mean value is found and considered as the pupil center. So from the pupil center and 3D eyeball center, a 3D line is drawn. Then the 3D line is projected onto a plane to find the point of intersection. The point of intersection is then linearly transformed to plot it on the screen plane to find where the viewer sees.